Alright, so we said that using those two equations, alpha, the solar altitude angle, and AS, the solar azimuth angle, you can plot this. This is kind of the trajectory of the sun in the sky. And you can do this this is done for June 21st. You can do it for any day. Okay, so I'm not gonna assign homework this time, but next week I'm gonna ask you to do this chart for Tulsa, Oklahoma in a bunch of days. Or even for all the, like February 1st and March 1st and April 1st and May 1st, so that you would see exactly where is the sun in Tulsa, Oklahoma every single day of the year. Now, there are two things that are weird in this chart, right? What are those things? Something you shouldn't really buy. You shouldn't believe this chart. This chart is not correct. What's not correct about this chart? No, that's okay. What's wrong is they say that the solar noon happened at noon, meaning the sun reached the middle of the sky, the highest point in the sky, exactly at 12 o'clock. Does this really happen? For obvious reason. Solar time is not our watch time. There's something called standard time and solar time. But the clear example is the day saving time. In the summer we move our watch 1 hour earlier, right? So it's not the same. So it will not happen at 12. It will probably happen at 11, right? That's one thing. The second is that symmetry also. Does it really happen exactly like this? So let's see. So what's the solar time and what is the standard time? It's basically this. It's the politics, or basically the fact that we divide the world into countries, right? And so those people living in one country, they don't wanna say, no, if it's 12 o'clock over here, it should actually be 11 a.m. over here, because we didn't have the sun yet. They cannot do this, right? So you can see China is basically all like one time zone, right? So everyone, when it's 5, let's all wake up. It's 5 everywhere, but it's not really 5, right? But it's just like we all decided to adjust our hour together, so that when we start a war and we are fighting Taiwan or something, let's all fly at the same time. You cannot have everyone basically having his own time zone. Of course, if the country is really long, like the Russia or like the USA, then we cannot do this. We have to have 4 time zone, because otherwise people in California will wake up really, really early for no obvious reason. Like woke up, it's 7 a.m. now in New York. But man, it's 4 o'clock. Why would I have to wake up right now? So when the country is really long, they divide it into basically time zones. But what is and you can see that the time zone is really, sometimes it's really political, like I want to be here, or like basically those people in Brazil say, or Argentina say, you know what, we are really not in the same time zone, but we want to wake up with Brazil because we are watching their TV, or they are we really want to wake up with them and sleep with them. That's basically how it will work. Okay? So like then it's Greenland, they decide, well, we don't have that many people anyway, so we are not going to split this into 3 time zones. Let's just have 1 time zone, and those people just will have to suck it up and wake up early. Or maybe we'll just, make those people spoiled and they have to wake up every day at 9 o'clock and go to work at 10. So what's the consequence for this? The consequence is that the people here in the central time zone, which we are in, only one place, one meridian having their watch correct, and everyone else basically have to adjust his watch to that time zone. Okay, so now where is that magic place in the central time zone that they have their time exactly correct? No, I'm talking about the meridian. So in this meridian, starting from Texas all the way up to Wisconsin, all the people in the central time zone, which place has their watch match exactly the solar time? So our longitude on Tulsa, Oklahoma is what, 95? I mean, if we Google Tulsa, probably we are 36 with 95. So in the central time zone, people decided, and actually all over the world, people decided that we cannot have France at 2 o'clock, and then England will have 3:15, and then Italy will have, 1:20. They don't do this. They basically decided that, guys, we just have to be 1 hour apart from each other. It will be easier to adjust our watch when we travel. It will be easier to coordinate with our stock market and stuff. So basically the world will allow you to have 1 hour difference. Okay, so the 0 is in Greenwich in England, and then you are Greenwich plus 1, Greenwich plus 2, Greenwich plus 3, and that depends on how far you are from that 0. So basically every 15 is going to be 1 hour. So obviously in the USA we are sitting at 75, 90, 105, 120. Those are the correct meridian. Only people living on 90 in the central time zone will have their clock correct. And we in Tulsa, if we are at 95, we are 5 degrees off. So we said every hour is 15 degrees. So every degree is how many minutes? 4 minutes. So if we are living at 95, we have 5 times 4, we have 20 minutes off. So when we close the lecture here at 10, it's not really real time or solar time. Let's call it solar time. Solar time is not really 10. It's actually, it's what? No. Yeah, it didn't come 10 yet because the sun didn't come to us. So it's 10 at those people. Actually, you're right. No, sorry, 10:20. Yeah, because it was 10 there and then they moved. No, back again. Sorry. No, we didn't come yet. So people in the east will have their time earlier than us, right? So if it's like 10 o'clock, 10 a.m. at 90, at 95, it's not 10 yet, right? We are less than 10, correct? So that is the first thing that screw our time. So we can, the equation is that the standard time and the solar time related to each other by 4 degree time, the difference between the standard longitude and the local longitude. What's your standard? 90. That's what you adjust your hour on. What's your local longitude where you actually live? At 95. And that makes the 20 minutes. And so of course those mirrors don't care about your standard time. They don't care whether you have day saving time or not. They care about the solar time. So all the equation for alpha and AS require the hour angle based on solar time, right? So then the problems in the homework and the quizzes become tedious when we say, where is the sun at 3 p.m. standard time? You're like, now I need first to convert the standard time to solar time so I can find out my hour angle, then I can use the equation. Make sense? All right. So the first correction is because the standard longitude, and the second correction is because, so actually this is the part where I say 90 and 95. So Tulsa, Oklahoma, use Tulsa, Oklahoma, 95 west and latitude 36. And I had a bunch of students before didn't understand what is this 9 prime and 14, what is that? That's 9 minute and 14 second. Then they didn't understand how to convert this into a degree because the equation requires an angle. So how you convert the second into minute, and how can you convert the minute to degree? Divide by 60. So 14 over 60, that's how many minutes it is. And so you got what, 9 point something, 9.3 minute? 9.3 minute divided by 6, you get the degree. Okay, that's how you convert the second into minute and the minute into degree. Right? So 90 degrees is basically going, someone lucky in Arkansas basically have his watch exactly matching the sun, and so every day is like, wow, solar noon, sun is facing south. Everyone else, is like, you have to, it's not going to happen at noon, it's going to happen either earlier or before. Right? Very good. So 75, 90, 105, 120. And so those, I'm not going to give you the standard longitude. So if I say calculate the solar hour in Florida, somewhere in Miami Beach in Florida, you need to know that the standard longitude for Florida is 75 degrees. Because Florida is Eastern Standard Time. Right? If I say California, it's going to be 120 Pacific Time. Utah, right, is going to be 105 Mountain. Alright, the second adjusting is because the day saving time, and we know why we have the day saving time. The north you get, the more north you live, the bigger the discrepancy between sunrise, between summer and winter. Okay, so if you are living in the equator, you don't see that. Sunrise and sunset happen almost the same time all year long, but you go all the way up and you get this big difference. And so people living in Michigan, they basically find out that, well, in the summer the sun comes really early, like it's basically you are in bed at 6 a.m. and man, the sun is outside. Why what we are doing here in the bed at 6 a.m.? They're like, but the work doesn't start until 8, what should I do? And so they will say, okay, let's do the day saving time. So they push every 1 hour, every one clock, basically say, you think it's 6? No, let's make it 7. Yeah, get out of the bed. And so you leave early, you go to work early, and you finish early. So rather than finishing work at 5, you're actually finishing at 4. So you leave home, you leave work at 4, and not only have 1 extra hour because you left work earlier, but also the sun is not going to go down until 9, right? It's not good. And so then you have a lot of hours because you left early and because the sun is always there. So then you have a lot of light in the evening, and then that basically, the series that it motivates basically a lot of economical activity. People are not going to stay at home, they're going to go to parks, they're going to spend money, they're going to work, do something interesting. And so but the bad side of this is that there is research on like this will basically screw up our biological hour. So if we live with the same clock all the time, it's much easier on our body than having this variation. Anyway, as far as this chapter is concerned, day saving time need to also come into the calculation, right? So if you are in summer, you have to chop 1 hour to come to the solar time. So you take correction for the standard longitude and local longitude, and you take another hour because of the day saving time, because you know that your watch is basically pushed 1 hour faster. Alright? Third correction, and that's going to be really weird. So here is the surprise. The sun is not at the center of the orbit. That's not a surprise. You know that. The sun is basically sitting up a little bit off. And so when we rotate around the sun, Kepler laws for physics basically say that this area needs to be equal to that area. So as a result, when the Earth is away from the sun, it moves slowly. And then when it comes closer, it moves very fast. Okay, that's fine. But what's really actually interesting is that the Earth's rotation around itself speed up and slow down when you are far away. And so here's the surprise of your life. The day is not really 24 hours. The day actually get a little bit shorter and get a little bit longer. As a result, we get this correction. It can accumulate to 15 minutes. Okay, so you think it's midnight, and you are celebrating your anniversary or birthday, it's not in midnight. You are screwed up in 15 minutes because of this. This is called the equation of time, or the e-correction. And that e-correction is coming from this curve. All you need to do is find out what day of the year it is, and you can find out how long your watch is. But don't panic yet. At the end of the year, the average hours per day is exactly 24. So the equation come back again to the same location exactly. Alright? So at the end of the year, you got like 4 minutes off, basically, the equation of time. Does this make sense? There is an equation, long equation to calculate this curve. So you are welcome to use the curve, or you can use this equation. Okay? What is the equation here? This is the E equation. E is 9.87 sine 2 times Bn minus 7 cosine Bn minus 1.5 sine Bn. What's Bn? 360 n minus 81, 360 over 180 times pi. N is a Julian day. Now what is confusing about this equation is, the question that everyone asks usually is, should I set my calculator to radian or to degree when I'm doing the cosine and the sine? And if you do the pi over 180, you see this pi over 180, that's to turn Bn into radian. Then your calculator should be into radian. But sometimes people want to set their calculator to degree, because I tell you what is the angle of the solar altitude angle, and you are doing sine minus 1 and stuff. You want everything to be in degree. If you want to do this in degree, then don't multiply by pi over 180. Cancel this pi over 180, and this number will be in degree. So basically what I'm trying to say is that they multiply by pi over 180 to turn this into radian. If you cancel the pi and 180, it becomes degree, and your calculator can be calculating everything in degree. You got that? Right. So this is how you calculate the E, right? And so the solar, here is the equation. The solar time is the standard time. So he said 3 p.m. Find where is the sun. I need the solar time so that I can calculate the hour angle. So I can use the equation. So in order to calculate the solar time from the standard time, which is 3 p.m., I do 3 p.m. plus 4 times standard longitude. What is the standard longitude for Tulsa, Oklahoma? What's our standard longitude? Well, 90. Standard longitude is 90. The local longitude is 95. So the standard longitude can be either 75 or 90 or 105 or 120. The local is the place where you are calculating those things. Are you doing it for Little Rock, or are you doing this for Tulsa or Oklahoma City or Dallas? That is the local longitude. Okay, and you see multiply by 4. 4 minutes. 4 minutes times the difference. That's in minute. Plus the E in minutes. And here is the E equation. Okay, and he's saying that if you are in the summer, if he said 3 p.m. in June 21st, calculate where is the sun. Obviously June 21st, that is having into it day saving time, right? So if it's 3 p.m., then the standard time is not 3. The standard is 2. So you write 2 as a standard time. You got that? Very good. You will have fun with that homework when you try to calculate that chart for Tulsa, Oklahoma. Alright. So after we calculate the correct time, the solar time, then we can calculate the solar hour angle, right? And we said 1 hour, 15 degrees. So 11 a.m. minus 15, 10 a.m. minus 30, 3 p.m. 3 p.m. would be 3 times 15. That's plus 45. Okay? So another confusing thing is that people think the solar hour angle tell you where the sun is. So if I said 3 p.m. and the hour angle is 45 degrees, they immediately imagine that the sun would be where? If the hour angle is 45 degree, where is the sun? Our angle is plus 45 degree. Where is the sun? They wrongly assume it's going to be at 45 degree over here. No. To find out where is the sun, you need to calculate the solar azimuth angle. You need to go to this equation. The equation for AS. And no one said that sine AS is sine HS. The fact that HS is 45 degree doesn't mean that AS is 45 degree. Because there is cosine delta and cosine alpha between them, right? But they just think, well, if the hour angle is 90, that means that also the azimuth angle is 90 and the sun is exactly at the west. No. The hour angle and the azimuth angle is not the same. However, having said that, there is relation between them, and that relation is if the hour angle is plus, chances are the azimuth angle also is plus, meaning that if you are above noon, the azimuth angle also will tell you that you are beyond the south, you are going to the west, right? And if the hour angle is minus, then chances are the azimuth angle is also going to be minus. But that's as far as the relation go. It's not going to go to be alpha HS is 15, then AS is 15. No, it's not. Alright? Very good. So, but what another interesting thing too is if HS is 0, what is that? HS is 0. When the hour angle is 0, that is solar noon. Yes. When HS is 0, alpha is going to be max. And AS is going to be 0. So that's one point that we know for sure. Anywhere in the world, when you are solar noon, your AS is going to be 0, your sun will be facing south, and your alpha is going to be alpha max. Is alpha max is 90 degree? No, it's not. Not everyone will have the sun coming from the top of their head. Okay? Who will have this? Only people living south of 23.45 latitude. But people above 23.45 degree, they never dream of having the sun on top of their head. The sun will always be high, but not 90. 80. You go up to Michigan, it's going to be like a little bit lower. You go to Canada, it's going to be a little bit lower. Right? Sun will never rise all the way up. That's why people up north, they have really very hard time with tracking the satellite, because the trees and the buildings in front of them is covering their view, basically. Okay, very good. So here's an example. Please calculate the solar altitude at solar noon. Solar altitude angle alpha at solar noon, alpha max for the day delta equal 23.45. That's June 21st, right? At 40 degree north. So we got the L, we got the delta, we got the HS. How much is the HS? How much is the HS? Solar noon? 0. So we can just go and calculate exactly the alpha. So he does this, right? Here's the equation for sine alpha, right? You put those number and you get it. Interesting, this is a little bit geometry. Basically, he's saying that if you set the HS, where is the HS? Here, to 0, cosine 0 become 1, and sine alpha become sine L sine delta plus cosine L cosine delta. Sine plus cosine cosine. Does this remind you of something? Sine plus cosine cosine. Sine A sine B plus cosine A cosine B. What is that? That is cosine A minus B. Okay? So then he's saying sine alpha equal cosine L minus delta for that particular noon condition. And so then alpha is 90 minus, if the sine equal cosine, if two angles have the same sine and cosine, that means they share 90 degree triangle. And so that means then that alpha is 90 degree minus this. So alpha max is 90 minus L plus delta. You don't need to memorize this relation because you have this equation in our book, and that's good enough. But this is interesting because that shows you then why people don't have alpha max equal 90. Okay? When people will get alpha equal because of their L. As long as your L is above delta S max 23.45, you're going to have something less than 90 degree. That negative will eat the delta, right? And you are not going to get 90 degree. So that's why people living above 23.45 don't get sun 90 degree. It's always less. Right? And now this chart actually, or this slide explained to us why people at exactly on 21st of September and 21st of March, why do they have alpha 0 at exactly 6 a.m. and the location for azimuth angle is exactly 90 degree. So when it's spring, the sun would be basically so obviously sun is coming this way, and this is in the dark, and so the people hit the sunrise when they move into that line, right? When you go from the dark to the bright, that's when you get your sunrise. That's when the day starts. Okay? So this, with this angle like this, that is sun is coming this way. What is that? Is that summer or winter or spring? That's summer. More summer. People in the south having winter at this point. So then you can imagine if the sun, rather than coming from here, the sun end up coming this way. Okay? So when the sun comes this way, you find out that the people that will see the sunrise is everyone living at that curve. And so that edge, because the sun is coming into the paper now in the spring. Sun will be coming like this. So everyone along this line, the moment they come from the back of the paper to the front of the paper, they will have their sunrise. And you can see that for everyone living on this place, the angle of the sun is making with you, it's exactly coming from the east. But it's not the case in the summer. Okay? Alright. So this also explains why alpha max is changing from different place to the other, and why we don't get 90 degree if you're above the 23.45. But the equation can explain that here as well. Right? So typical problem. Find the solar azimuth angle on summer at 42 latitude from 10 a.m. to 2 p.m. So what he's doing is that he's asking you to do exactly the same but for different hours, and that's going to be the homework not next week, but the week after that. So starting from 10 a.m. to 2 p.m. find out where is alpha and AS. So here's your two equations, and those time, solar time, if you assume those solar time, you convert them to our angle, and you use our angle with the L and the delta to calculate the azimuth angle. Right? Make sense? Very good. Of course, if this was not the standard time, if this was not the solar time but the standard time, you need another correction between the two of them. Okay? And so we saw last time when we started this part, we saw only one curve in June, but now here are all the curves throughout the year, and this show you again. This was done for the 21st of every month for Mississippi State University, and so that 90 degree This is the azimuth angle and this alpha. This 90 degree happen only on the 21st of March and 21st of September, where it will come at 90 degree. And all winter it come less than 90 degree, and all summer it come above 90 degree, or basically coming from a little bit the north. And you can also see this 690 degree happen at 6 p.m. and 6 a.m. exactly. But in the summer the sun come earlier and set later, and in the winter come a little bit late, like after 6 a.m. and it's set before 6 p.m. So it sets at 4, for example. Okay, questions? Very good. So this chart, alpha against AS, can be plotted like this, but they also sometimes they plot them as a circle like this. So that circle, you can imagine this circle as basically the projection of the sky on top of your basically horizon. So you will be standing over here, and this is your north, this is your south, this is your east, this is your west, and this is kind of the trajectory of the sun. Okay, so at any, this is those lines represent the hours. So solar noon here, 11 a.m. here, 10, 9, you know. And so if you know the hour and the day, each one of those lines represent the day. Then you can basically tell where is the location of the sun, the azimuth angle, and this is the circles over here represent the altitude angle. So if the sun is over here, that's 90 degrees, it's coming from top of your head. But it's basically over here, that means it's like, say, 20, this is 10, 20, 30, 40, 50, 60, 70. Okay? So if you look to a chart like this, and I know the lines are really very hard to see, but if you look to those lines, this is again what, 90 degree and fall at 90 degree. That's exactly the spring, 21st spring and 21st March and 21st September. But look at the summer. What do you see? Never sets. The alpha never go less than 0. So that must be in the Arctic. That's 66.5. Okay, so then in that particular day of the year, then the sun never set on them. Okay, and correspondingly in the winter, there is one day in the winter where they don't really have the sun. The sun is like phew. Okay, very good. So the sun come at what time? It will come at 11:50 a.m. and it will fall down at 12:10 p.m. You got the day is only 10 minutes around noon, and that's it. There's no more sun. All right.